All right, we are live.
So let's go ahead and get started. So this talk is called Python Prying, Fun Security and Cryptography Demos You Can Build Too. So
Right,
I'm going to introduce myself first, although I know a couple of us did get introduced. My name's Josh McIntyre. So this talk is called Python Prying, Fun Security and Cryptography Demos You Can Build Too. So I'm going to introduce myself first, although I know a couple of us.
On the side, I'm a tech educator with my name's Josh McIntyre.
So this talk is called Python Prying, Fun Security and Cryptography Demos You Can Build Too. Cybersecurity, digital currency. So I'm going to introduce myself first, although I know a couple of us.
On the side,
My name's Josh McIntyre. So this talk is called Python Prying, Fun Security and Cryptography Demos You Can Build Too. Cybersecurity.
Apologies for that. Just wanted to make sure I was live.
Alright, so let's start again. So I'm Josh McIntyre. I am a software engineer at Microsoft Pittsburgh. Day to day, I write code for a cloud storage product called Azure Managed Lustre, if you're familiar with large parallel file systems. And on the side, I have a project called Chain Toots, where I'm a tech educator, and I create this kind of free and open license content about cybersecurity, cryptography, digital currencies, computer science topics of all sorts. So I have the YouTube channel, I have articles, code, and my new book as well. And everything's Creative Commons license, BSD software licenses, so I highly encourage reusing things, sharing things, redistributing, including the book is actually CC as well. So, also a little bit around once a month, I volunteer with the Cryptocurrency Certification Consortium. They're a nonprofit that does this kind of open educational material about crypto. And it's more focused on the tech side, security, keeping yourself safe, not some of the other stuff with crypto like the gambling and all of that. So outside of what I do with computers, I'm super active. Garrett and I bond over our love of jiu-jitsu and MMA, and I'm a climber as well. So why Python? Why this talk? What are we going to be doing today? The reason I love Python is because it's such an excellent, versatile tool for all sorts of software development. And it's really good for security, it's good for automation if you're an IT person. Python's really easy to use, it's really fast to develop with Python and iterate on your projects because it is interpreted, so you don't have to make one change and wait 20 minutes for it to compile. You can kind of do things fast. And the syntax is really friendly. So the whole goal for this talk, this isn't like necessarily a step-by-step guide on how to do all 6 of these demos, right? That would be a 6-hour talk and I'd be tired and everyone would be bored. But what I really want folks to walk away with is the inspiration to try out your own projects, to tinker a bit, see what's possible with Python, talk about some really interesting security topics and cryptography topics, and get to work on something that's of interest to yourselves. So there's 6 demos I'm going to go over today. And like I said, I'll move kind of quick through the demos. I'm more interested in talking about the security and some of the neat libraries and things than necessarily being a step-by-step guide on these. But first we're going to start with some demos, educational demos of some real-world malware that I've seen in the crypto space. There's a couple concepts of attacks that have happened to real people that have caused them to have money stolen. And it turns out, at least without doing all of the obfuscation and very sophisticated things that real malware does, these demos are actually really quick and easy to cook up, so it's kind of cool and a little scary. I also have 2 hardware demos with me today. Both are written, even though they kind of look like Arduino, they're both written in CircuitPython, which is Python for microcontrollers like this. One is a very basic hardware wallet demo for digital currencies like Bitcoin. And the other is a demonstration of what we call proof of stake consensus in digital currencies like Ethereum. A couple years ago at a conference in Denver, I did a visual demo of proof of work, so now I'm doing proof of stake as well. And the final one is another fun one that's fairly recent, and this is a demo of a path traversal software vulnerability. So this one will be a demo of a actually fairly common vulnerability that web software sees, and we can talk a little bit about how to mitigate those vulnerabilities if you're a developer. So the sources are all available at github.com/chaintoots. I have a QR code over here as well if you want to download the sources, modify them, share them, anything that you want to do. It's all open source, so I highly encourage taking some of the code and running with it if you have an idea for something else. So the first two that we're going to talk about are very similar. These are what we call seed scanning malware. So how many of you are familiar with cryptocurrencies at all and how they work? Yeah, it's a really interesting field. It's really neat, open forms of money. So, without getting into all of that, digital currencies like this are basically just protocols for exchanging value the same way that the internet is a protocol for exchanging information. So Bitcoin, Ethereum, Litecoin, Bitcoin Cash, there's thousands of them. They're all what we call open blockchains, which are a bunch of people around the world run software, and they all agree to the rules of that software. And there's cryptography that's used to reach a consensus about what transactions are valid, and you can exchange value without having to have like a bank or a credit card company in the middle. Make sense? One of the interesting things about crypto is that you store private keys for your digital currencies kind of the same way you do for other instances of public key cryptography. So I would guess most folks in here are familiar with TLS for a web browser, right? Your computer generates a private key, it gives a website a public key, there's an exchange that happens that allows you to encrypt the traffic between you and your web browser. Very similar concept in cryptocurrency. What you have is you have a set of private keys, and you generate public addresses that people send your money to. So in this case, it's different than a credit card number, which is a private value that you give to the merchant, and you give them permission to pull funds from your account from that number. With crypto, the person that's receiving the money, like a merchant, gives you their public address. And you have some value, you use your private keys to sign a transaction, sending that value to now it being owned by their public key. Everybody understand that? So there's kind of a problem with this, right? You have to keep your private keys safe. That's rule number one in crypto. If you lose your private keys, if anybody gets a copy of them, they can clean you out, no problem. So it's a very powerful technology, but it can be very dangerous too if you make a mistake. It used to be that wallets would just generate a bunch of individual keys at random. And this was a huge problem for backups because now you have to back up hundreds of keys in a file. As you run out of addresses, as you keep using them, you need more. So years ago, the community came up with what we call a seed phrase. And all this is it's a way to encode a master private key in 12 to 24 English words. So now, if you are using a crypto wallet for the first time, you spin up your wallet and it gives you 12 to 24 words that you write down and back up, and that's what you keep safe. And if you drop your phone in the toilet, if your hardware wallet breaks for some reason, or you have any issue, you can import that seed into any other wallet that supports the standard. So it makes backup super smooth. Downside is, that's a really, really juicy target for attackers. Sorry, I know that's a lot of context on crypto, but I wanted folks to understand it. Yeah.
What year did they start that?
Around 2014, if I recall correctly.
Okay.
I want to say it was around 2014, and between 2014 and 2015 is when they really became kind of the common standard. I might be getting that wrong, but it was at least a few years after sort of the initial
That
wallets.
was for Bitcoin wallets also?
Mm-hmm.
Okay. I'm only asking because I have a Bitcoin out there that I can't bring.
Yeah.
That sucks.
Yeah, it does. And there's really no way to brute force the key to get it back if you lose the keys.
I looked quite a bit.
Yeah. Yeah, there's a story about the guy that's trying to convince a garbage dump to go digging for his hard drive that contains millions of dollars.
Yeah.
And it's like, I'm sorry, brother, you're not going to find that now. So anyway, all that context just to get folks familiar with digital currencies because they're sort of a topic of a couple of these demos. And the first one is seed scanning malware. So like I said, your seed phrase is 12 to 24 English words. And they're specific words that come out of a 2048 word dictionary. So we know what the words look like. We know what the dictionary is. You can start to find a pattern, right? And what are computers really, really good at? Searching for patterns. So, this is a real attack that's happened against crypto users. And one particular real-world example was found by, I believe, Kaspersky Labs, and it's called the SparkCat malware. So, this particular one is really cool because it attacked mobile phones. And what it would do is the app would pretend to be something like a food delivery app or a chat app. And in the background, the code would scan your photo library and use OCR to pull out the seed words and match the pattern. So that's what our demo shows. So not only can you scan for these seeds in text, you can also scan for them in pictures. So these two demos are both variations on the same theme. One searches for the seeds in text files, the other one in OCR. So that is OCR seed swipe and seed scanner on the J2's GitHub. So let's talk a little bit about the basic code for this in Python. The first tool that we'll talk about is regular expressions. So how many folks here have played with coding and are familiar with a regular expression? Yeah. So a regular expression is essentially a language for expressing pattern matching capabilities in code. So they're really, really common for things like a website validating that you put in a valid phone number or a valid email address. There's all sorts of general use cases for them. And in this case, what we can do is compile a really big, really unwieldy regex using our seed word dictionary. So there's a standard word list for what we call bit 39. That's the standard for these mnemonic seeds that popped up in around 2014. We can combine all of the words together in sort of an OR statement in our regex. This is a really unwieldy way to do it, but it works. It's relatively fast. There's more efficient ways you could do this as well. And we build our regex to look for all the combined words and 12 to 24 of them in a row. And we factor in white space as well, so that's the /s. So once we compile our regex, we can then start to scan our file system for these seeds. So we can compile a big list of files on the target computer, and we can go through each file and just do, in Python, a match. So this will pull out, I think in this case it's a regex.search, but I'd have to look at the full source for that. There's different variations of regex that will either match specifically from the beginning of a string or anywhere in the string. The anywhere in the string functionality in Python is the regex.search, and you would use that for a case like this, but it's slower. If you know your pattern is likely to be at the beginning of a string, like a phone number or a log file, match is a little bit quicker. Now what about the pictures though? So who here is familiar with OCR? Yeah, optical character recognition. Again, this is actually a really common programming tool now, for accessibility reasons, for efficiency, if you're scanning a large batch of documents into a computer and you want it to be searchable and modifiable, you can use optical character recognition. And in this case, Python has a really handy common library using Tesseract, which I believe is maintained by Google now. I need to double check on that. So you can use Tesseract to pull characters out of an image. So it says, find me all the words in this image, recognize them, and pull them out into a string. And then we just feed that string to our pattern matching regex. So I find this attack really, really interesting because, looking at the code, that's only a snippet of it, it's not the full code, but it's pretty simple. The hard part is doing all the real malware things, obfuscating it, getting it onto target devices, keeping it hidden. But it's not hard to search for something private like a seed phrase. You could modify this to look for SSH private keys, or a GPG private key, any kind of string encoded private data. If you can get that code onto the target system, you can get that private data out. And in this case, if you get that private data out, you can steal somebody's money. So, crypto's a really interesting industry to be in if you're talking about security, because it's essentially a giant bug bounty where you don't have to convince the company to pay you if you're malicious. You can just crack the bug and then take the money. And it can be reversed. So bonus on this front, talking about regexes and malware, is another very interesting digital currency attack that we call address swapping. So I talked about before how when you go to send somebody crypto, you give them a public cryptographic address. Spoiler, that's a long random string, and they're really hard to deal with. They're really hard to type. You can't memorize them unless you're like a memorizing savant. So what most people do to interact with crypto is they either scan a QR code on their phone, or if you're on a PC, you use copy and paste. So if I want to send, say, from my PC wallet to my exchange so I can swap cryptos or cash out to US dollars, I'm probably going to copy an address from the website and paste it in my wallet. And one of the interesting malware attacks out there for this is to detect the pattern of a crypto address in the clipboard buffer and replace it with an attacker address. Because most people, especially if you're in a hurry, you're not going to double check that address exactly. So you copy an address thinking you're going to paste your address back in and do your transaction. And in the middle of that is this malicious code, which swaps it out with an attacker address. And if you're not paying attention and you paste that, then you send the coins off to them instead of your intended recipient. So this is very similar. We have a pattern, a regex definition here that I had to do in an online regex editor because nobody gets a regex right the first time. I certainly don't. And we have our malicious address. This isn't like really a valid Bitcoin address, but for demonstration purposes. All we need to do this in Python is have our regex and then use the paperclip module from Python. And so we can just enter a continuous while loop, search the clipboard for our string, pattern match it and say, is this a Bitcoin address? And if it is, put our malicious address back in the clipboard, and then sleep for some amount of time so you're not eating up all the CPU on your target system and making them aware of this. So these are all some pictures of this, these different attacks. I put a demo on a Raspberry Pi, made a GUI with this, command line, Python library, and demonstrating this sort of copy-paste attack on this website. So I copied an address and ended up with this when I went to paste. So these are all Python. The Adderjack one also has a C# version that I did, and then added the Python version on. So I'll stop there and take a breath. I'm saying a lot. Anybody have any questions on these types of attacks and sort of how we work them?
A similar attack to the one you just showed, what they do is they'll take the first few characters and the last few characters, keep them the same, switch the middle, and then that would be the address that they send it to. Because
Yeah.
people can only, you look at this string, they'll check the first couple last, and then hit send. So that's the latest one that's out there.
Yeah, you're absolutely right. And I forgot to mention that is part of this attack is a lot of times the really sophisticated malware will try to match the first couple addresses, first couple characters of the address. The last characters can be harder to do because it's a cryptographic checksum of the first part of the address, and so there's more computation required to get that right. But that said, you're right to point out, when you copy and paste, a lot of people are at least somewhat wary, oh, did I make sure I paste the right address? They'll check the first couple characters and then skip over the rest. So I highly recommend if you're doing large value transactions with a digital currency, you should check beginning, middle, and end of the address when you paste. If it's a lower value transaction, check the first two, check the last two, a couple in the middle. But these are really interesting and scary attacks, and the thing that I love about these demos is this is real. This is stuff that's actually happened to people. I actually had a client reach out to me that downloaded game cheats or something like that and got the address swapper on his computer and unfortunately lost some Ethereum. And that's mentioned in the book in the part about the threats.
So I guess North Korea is probably using this too, since the gloves are off.
I'm sure. I mean, yeah. I don't remember who SparkCat was, if they attribute it to anybody, but it was targeting food delivery and chat apps, I think, in China first, and then a couple other places.
Yeah.
All you need is one person that's not paying attention, and you start getting the rewards in an irreversible currency. So it's a little scary. Gary, can I ask you a favor? Could you grab a picture or two?
Yes.
Just grab a couple. Thank you.
The other Rob was here, and he's got plenty of pictures I could share with you as well.
Thanks.
Yeah.
Yeah, just a couple so I have some high quality. So the next ones we're going to talk about are a couple, not security as much, but cryptocurrency and blockchain cryptography demos. And these are really interesting because they show some of the inner workings of these currencies. I just so happen to have a lot of these demos about cryptocurrencies because that's a lot of what I do for my education efforts, is how all of the security and cryptography stuff ties in with this. So our first one is going to be an educational demo of a hardware wallet. I mentioned, of course, the seed phrases and the transaction signing and some of the dangers of having your keys potentially exposed on a device. So a very common tool now for crypto users is what we call a hardware wallet. And these are commercial microcontroller devices with a screen that you can buy that generate and store the keys offline. So the keys never touch your PC or your phone or your network device where some of these attacks are prevalent. So they will sign the transaction on the device itself and send that signed transaction to your PC that when you plug it in, but the keys are never exposed. So my demo, Microbit Adder 2, is a very stripped down version of that, and all it does is it generates a key and an address pair. So you would have to manually write down the key, and if you want to spend, you would have to later import that into a wallet with more functionality. But it kind of demonstrates that general concept of a hardware wallet, and it's on off-the-shelf hardware you can get from Adafruit. The other one, StakeSim, is about proof-of-stake consensus. So this is a particular way that users on the network agree which transactions are going to be validated. instead of having the bank or the credit card company in the middle. So that's Microbit Adder 2 and StakeSim on GitHub. So the hardware wallet one is kind of one of my favorite projects that I've worked on. The hardware wallets are preferred for high security self-custody. So if you're going to hold your own keys and not have an exchange like Coinbase do it for you, generally want to have a hardware wallet for anything more than you're spending money. So the retail versions are those full-featured ones. They'll sign transactions. They support a whole bunch of currencies. But a hardware wallet can be as simple as a single address and private key pair that we generated offline somewhere. So it could be an air-gapped laptop that you rip the network card out of. It could be a commercial hardware wallet, or it could be something like this. Because this microcontroller is not an internet-connected device. You would load the code from your PC, which I guess could be an attack vector theoretically, but it'll generate the keys for you offline for you to write them down on paper, engrave into metal, and safe keep them. And I should mention too, you have the public address, so you can send any amount of money you want to that public address, which is recorded on the blockchain, which is the public transaction database. You don't have to be connected to the internet to receive to an address. You only have to be connected to the internet to send your signed transaction to someone else. So the first iteration of this, I presented at the DEF CON Blockchain Village in 2020 remotely, and this iteration of that project was done in both C and CircuitPython. I had a really hard time at that time finding the right cryptography libraries that I needed to generate an address. So I used Trezor Commercial Hardware Wallet's C source code, because it's open source, and made my own CircuitPython module that then I could interface with all the stuff for the screen and the easy scripting side. But I really wanted to try to do it in pure CircuitPython. I mean, Python's just cool. It's just super fun to work with. It's one of my favorite languages. No hate on C. I love it and use it too. But I wanted something where I could write the code to generate an address and just load it on one of these in 5 minutes and have it work. So that's what our demo does. We generate a private key and address pair using pure CircuitPython.
Why CircuitPython?
I just think Python's way easier to work with, honestly.
Yeah. No, I mean like CircuitPython. What is that? Versus regular Python.
I should add that context, thank you. So, Python is an interpreted language, right? You have to have a Python interpreter to run Python. And the main one that we use all the time is usually CPython that you install on your PC, your Raspberry Pi, and all that. A microcontroller like this does not have the storage and the processing capability to run standard off-the-shelf Python. There's an older generation of a Python interpreter on these small devices called MicroPython. And CircuitPython is just an enhanced fork of that MicroPython interpreter. So the only reason for that is CircuitPython is just a really stripped down version of Python that's able to run on these small devices. So one of the really tricky parts with doing this particular project was, how do I get all the libraries I need? In normal CPython, there are a lot of libraries that you can get from pip, the package manager, and many of those, especially when it comes to cryptography, actually run C code. Like, they drop down and run compiled C code. So you download the package, it might have to compile that, or it might already have binaries that can run for Windows, Linux, Mac. But in the hardware world, no one can hear you scream, right? There's a lot of considerations to even being able to get a basic program to run on one of these. Now, things like CircuitPython, things like the Arduino libraries do make it easier, but it can be tricky. So I was able to find several pure Python cryptography libraries to run this code. Without boring everyone to death with all of the mechanics of Bitcoin, there's a couple things that we need. First is we need a way to generate true random numbers, not just pseudo-random. If we're generating a cryptographic key, we have to have a cryptographically secure random source. Thankfully, the Adafruit platform that I used has one built in. The M4 line of microprocessors has a CSPRNG built in, and you can just use os.urandom like you would on a PC. We also need an elliptic curve algorithm for our public key crypto. Bitcoin in particular uses elliptic curves, and it uses the SecP256K1 curve. It's a little bit of a niche curve, I guess, in the crypto world. It's not as common for things like certificates, but it has some properties that make it really efficient for processing transactions on the blockchain. So we needed that, and we need two hashing algorithms along the way. We need SHA-256, which is really common, and RipeMD-160, which is not so common. So I had sort of the challenge of having to find all these cryptography libraries and get them to run on CircuitPython, which a couple of them did require some minor tweaks that I was able to check into my code base, because they're all open source. So we start with our private key, we get our public key, and then to generate our final address, it's not just a pub key, it's actually a hashed public key. So we end up going through 2 rounds of hashing, one with SHA-256, one with RipeMD. We calculate a checksum to add to the end of our address, and then we encode that using base 58, which is similar to base 64 with a couple characters removed, and those characters are ones that are easy to mix up. So it's sort of designed for readability, since Bitcoin, that's really, really important. Did everybody kind of follow the rough sketch of how that works?
Characters can get mixed up with base 64.
I don't remember off the top of my head which ones are stripped out, but I can find out for you.
It's like the upside down E looks like an E, and it's because it's ASCII, so it's those characters that are non-alphabet, non-numeric characters would be the ones that look like an L for a numeric character.
That's interesting. You probably could use that for finding people using base 64 for these keys. Excellent.
Yeah, but the general idea is to sort of talk about the cryptography here, right? How do you make crypto run on a small device? And there's one really, really important caveat I do want to bring up with this demo. In general, for production, really secure code like generating a Bitcoin address in a hardware wallet, Python actually isn't really the tool that you want, at least not pure Python. Because there are attacks, because Python is interpreted and it's kind of slow, things like side channel attacks, you could theoretically extract keys during the process of creating the address or signing a transaction using Python. I'm not an expert on those kind of attacks, and I don't want to bungle how that all works by trying to talk about it too much. But essentially, there are actually reasons you would want to use C or C++ to do production cryptographic code. But on the educational front, it's really, really interesting to be able to do something like this in pure Python. I mean, I found it fun to try to get all of the crypto that I needed loaded onto a tiny device in pure Python for this kind of exercise.
Did you try the light bulb analogy for a side channel attack? You have 3 light bulbs in the room, the old-fashioned, and you tell the person, how do you tell which one was on, but you can't see in the room, and then some people say, oh, you go and you feel if it's hot, so you're kind of like doing a side channel attack there where you're guessing which one was on. So
that's actually a really good analogy. Yeah. I have to keep that in mind.
You're guessing, right?
Yeah. Yeah, I mean, the point is, if you were going to make a commercial hardware wallet, pure Python probably isn't the right language to do all of these operations in because of those considerations around side channel attacks and Python's interpreted nature. Someone with more expertise at that level could tell you more. So in that case, you would want to do something like the first iteration of this, which is have the actual cryptography operations drop down into C and be highly optimized, reviewed, scrutinized. The challenge that was very interesting here is, in order to get a pure Python version running, I had to find pure Python libraries that people had done for educational reasons, or they had a use case where it was deemed okay, I guess. Because most good Python crypto libraries are going to drop down into C, and I couldn't just pull those libraries in and get them to run on this without all the compilation steps. So, food for thought if you're ever doing this kind of thing in Python. And let me pull this up here as well.
Are there ever any problems when you drop down into C with Python?
I think there can be, in terms of, you have to get it to compile on all the platforms you want to distribute on. So, like, your build process is going to be more complicated. But yeah, just to show this demo, this is just a LCD character screen hooked up to an M4 microcontroller. And it just rotates through the private key, which is in wallet import format, and then the address, which is your public address that you would load your money into. So I've tested it. I've actually made sure these addresses are valid addresses and everything by plugging them into different tools. It's really interesting. There's a lot of moving parts, actually, to something as simple as basically how do you get a crypto address.
How many lines of code?
That one I want to say is probably in the hundreds, like somewhere, if I had to just guess, 200 to 500 lines.
Okay.
And some of that's other people's libraries too. I think what I wrote is 200 to 500 lines, plus libraries. So the next one we'll talk about is simulating proof of stake. I know this is all a lot of context in digital currencies. Who here is familiar with the terms proof of work and proof of stake? A couple folks have heard of them. Who here has heard about Bitcoin mining taking up a ton of electricity, like the electricity usage of a small country, right? And how that's somewhat of an environmental concern. Is that a concern around worthwhile use of resources? That's a debate for another time, I'm sure. So that is called proof of work consensus. Essentially, a bunch of people are doing a bunch of hashing operations in order to find an output that meets certain guidelines. It's a really, really simple bulletproof system to get everybody on the network to agree who gets to validate all the transactions. Because we don't have a bank, we don't have a credit card company in the middle saying, Jeff's transaction can get in, Doug's isn't valid, who's going to get processed now? So several blockchains have come up with alternatives to this that are much more lightweight in terms of computation. The second largest crypto project is called Ethereum. It has a lot of different capabilities. And Ethereum is noteworthy because it originally used proof of work and transitioned it to what we call proof of stake. The essentials you need to know about proof of stake is, instead of everybody putting a bunch of computing power into the network, instead they put value in, like collateral. So you don't have to have big server farms to do proof of stake, but you do have to have some money to start with. The essential way this works is that everybody that wants to potentially validate transactions and get the reward for doing so puts up some stake as collateral. So maybe you put up 32 ETH, which is the minimum. He's got 256. They don't have to be even numbers, but there's a minimum of 32. And you get punished if you try to do something malicious. So the rule set that everybody's validating says, oh, if you're the staker and you try to get in transactions that you shouldn't have, you lose some of your stake to the network. It's a punishment. They call it slashing in Ethereum. And I'm not an expert on this type of consensus, but what's very interesting for our demo is how do we pick which validator gets to win the race? How do we pick which validator gets to go through all the transactions? We need some random way to do so people can't just game the system. In proof of work, the randomness is done by the nature of SHA-256. So everybody's trying to do a bunch of guesses to see who's going to get that value that matches, and then everybody on the network can see, oh, okay, Tim over there he got the right number. Everybody can validate it really quickly, but it took him a lot of computation to get there first. With proof of stake, we don't have that computation going in. We don't have the random distribution of SHA-256 to guide us in picking a person in a way that can't be gamed. So we use a really interesting system that is called commit and reveal. We need to be able to pick a random validator, but we don't. How do we generate a random number and avoid somebody's computer like getting hacked or gaming the system? So I should probably ask at this point, and maybe it's too late to ask, is everybody here familiar with the purpose of a cryptographic hash function? Fairly familiar, right? Essentially, you have an input, and you get a random output that's the same every time. So it's deterministic, and it's one way. If I put hello into SHA-256, I get the same hash value every time. And there's nothing in that hash value that gives me any hint whatsoever the original input was hello. That's what makes it a cryptographic hash versus like kind of hash function you would use for coding a hash table or something like that. So what we do in our proof of stake scheme is everybody that has a validator that's running this code generates a random number on their computer, just using their crypto random source like os.urandom in Python. Then everybody hides that random value behind a hash. So they take their random number and they put it through the hash function that the rules specify, and they commit that to the blockchain. So at a certain point in time, they say, this is the hash of my random number. Then we do another round where everybody on the network reveals what their original number was. And now everybody on the network can confirm that that was correct. Because now that you have the input, you can put that through the same hash function and see that the originally committed output is the one that you expect. But at that first part, where everybody just puts the hash out there, you can't go backwards. There's no way to know just looking at the raw hash that what the original value was, unless you guess, which is kind of what proof of work does. So we commit, and then we reveal, and we combine everybody's random number together, and we use that random number to pick which validator gets to win this round. So the important thing here is we need to randomly pick someone out of this group of 7 people or 6 people that's going to validate this batch of transactions. Whoever does the validation gets a reward for that. They get transaction fees and they get newly minted coins. And so there's an incentive for people to try to game the system, right? You want to, if you're a validator, you want to try to break it so that you get picked every time and you get to make a ton of money. That's why we need these kind of consensus rules. So we do the commit, reveal, and selection process so that nobody can game the system and make their random number work in some way that results in the final pick being them. Does that make sense? This is the one that I was the most worried about explaining because there's a lot of moving parts.
Yeah, I feel like I'm missing a step from where you consolidate the revealed values, and then how does that lead to a selection of anyone?
So as far as I understand it, and at least in the demo, You literally just take all of the random values and you do a bitwise XOR to put them together. So the way that the final numbers are all put together is, the rules are there so that anybody can follow them, right? The problem comes in, the reason we have to do the commit first is, if I can see everybody's random number, and I know that the last step is going to be to XOR them together to get the final value, I might not actually pick a random number from my computer. I'm going to do a calculation so that if you add my value in and you XOR it with all the other ones that I can see, I get picked as the winner. And so that commit stage where we hide it behind the hash is done so that nobody can try to put a random number out there that works in their favor. Does that make sense? That answer your question? So to simulate this in a really simple way, we can just make a very simple 8-bit hash. And all this hash does is just does some XOR and modular arithmetic so that we get a value from 0 to 255. And our commit scheme in the demo would work just by running our random 8-bit value through our 8-bit hash and committing it. And then everybody does the reveal at the end. And all that this demo does is it shows what that process looks like visually by showing 3 random nodes, their initial commit values, their revealed values, their stake and how that weights them, because the more you stake, the more there's also like a weighting process that goes into that final number. And it shows our initial entropy and that sort of thing. So all this is designed to be is a simple visual demo of how that process works. I did the proof of work one with LEDs, where LEDs would light up and show you doing all your guesses in each individual hash output until you got one that met the criteria. And that's on YouTube as well. So sorry, I know that's a lot. But the takeaway is, I think these are some really fun ways that you can play with Python and do cryptography, work with blockchains, work with security concepts, see how these all work. You know, all of these took some time and work for me to put together, but they were fun. And they end up with something that allows other people to understand these kind of complex concepts a little bit more easily. At least I hope. At least hope everybody's not really confused right now. These could all sort of be their own separate talks, and some of them kind of have been their own talks. But I want people to walk away with that bit of inspiration and understanding of how you can use Python for this stuff. All right, so our last one before we get to Q&A and chit-chatting for as long as we want to. Path traversal. So there's a lot of ways computer software can be vulnerable. We're all security-minded folks in here. We're all software developers, different walks. One of the interesting ways that software can be vulnerable is in handling user input incorrectly. So this particular demo is a class of vulnerability called a path traversal. This is essentially bad processing of a user-given file name or file path on a system, right? So everybody here is computer folks. You know how you have directories, you have file names. And generally, there's a way for you to move back and forth, // to say move up a directory or down a directory in the tree. So this demo is called Path Prowler, and it's all Python. And it's actually an intentionally poorly written piece of web server code that shows how this works. So it's very common for a web server to have to process paths, right? When you go to a website and you have a URL and you have a bunch of slashes and sort of subdirectories in there, like maybe you have your to-do app and you have add slash delete slash complete. You could organize them into folders and those sorts of things. So let's propose a sample web app that takes a resource name in the URL and puts it in the path. And the server processes that path to go look for a resource, right? A web server at the end of the day is really just someone else's computer that gives you copies of files and gives you to them in a way that's nicely formatted that you can read in your web browser. Web servers also have things on them that we don't want other people to have access to, right? We have our web server folder that has our nice informational website in it, but our web server probably also has a TLS key, for example, to encrypt our traffic, or it has some other secrets on the server. So what happens if we take user input that's maliciously crafted to try to get at those resources in that tree that we don't want people to have access to? So our demo is a simple software vulnerability and security information database. It takes a database name and it spits out a nicely formatted table for you to read in your web browser. But it's got a fatal flaw. You can also use it to dump the server TLS key. So let's jump ahead to the example because I think this makes it a little bit easier to see. So if I give it the file name vulndatabase.json, it processes this JSON file and prints it out as a nice table. So we have our table talking about buffer overflows and cross-site scripting and path traversal. If we give it malwaredatabase.csv, it gives us some hashes of known malicious files and their names. And these two names happen to be for two of the demos we talked about in the first part of the talk. But what happens if we craft a malicious path and give that as our file name? So in this example, I've added two ... slashes, which work backward out of the web server root. And I've just tried, okay, /secret/cert.key. And my little processing script that either takes the CSV or the JSON and puts it in a table has very nicely for us dumped out the contents of our private key. So the key takeaway here is we should make it so that our code only certs files from our intended web root, wherever we're storing our website files. You shouldn't be able to work backwards anywhere else in the file system and get information as the client. But in this case, we don't handle that properly, and we do allow this backwards traversal. So what's the code for this look like? Now, I want to make sure I point out here, this is intentionally vulnerable code, so don't use this. This is bad. In this case, all I'm doing is I'm taking my template that I got from that parameter in the URL, and I have my resource directory, which is supposed to be my intended directory that has all my database files in it, and I just put the paths together. So I combine the directory with the given data file. And where the vulnerability lies is that here, I'm not doing any escaping or any sort of sanitizing of that input to make sure that if a user gives me a malicious file name, I don't actually process that malicious file name later. So in good code, what we want right here is some code, some logic, or a library that says, no, you can't use ... not in my house. Or does something like it generates the path with whatever it gives you, and then it double checks that resolved path and says, okay, the final path that I got when I processed all the ... slashes is not in the folder that I want it to be in. It's not in the allowed web root, so you can just throw an exception, return a 404, 403, say not authorized, sorry, you can't read my server key, before all this sort of processing and return happens. So this is just an example of the kind of things that you can learn and tinker with Python. I spent a couple weeks working on software vulnerability demos in a couple different languages. Python happened to be one of them. What I really want everybody to get the takeaway is it was actually pretty quick to iterate and come up with these demos and share them with people and have them be fairly straightforward to understand. I have lots of demos in other languages too, everything from C and C++, C#, Java, Rust, JavaScript, Go, PHP, a little bit of everything. But Python's one of my favorite to work with because it allows this iteration to happen really fast. It runs on a wide variety of platforms like a PC, a Raspberry Pi, a microcontroller. It's a really powerful tool for everything from these kind of standalone demos to enterprise-grade software. So I know I packed a lot into this talk, very hands-on, and I just kind of want folks to walk away with some of the interesting things that you can do with this language, with some of these interesting security concepts. So I want to encourage everybody to kind of go home and tinker with some of this stuff themselves. You don't have to wait for somebody to come up with a cool demo that you want to see. A lot of this stuff can be done in a weekend with a little bit of experience and a willingness to wade through some of the interesting things that crop up when you write software. So before we get to Q&A, I just want to end with where you can find me, where you can find my stuff. So chaintoots.com is my main website, and it really is just aggregates all of the other places that you can find my content. It has a contact form as well. But I'm mostly on GitHub for the code, articles, and the open source version of the book. That's where you'll find all the code from today. You'll find tons of articles that usually accompany the videos that I do. And you'll find the slides from today and more. YouTube.com/c/chaintoots, that's where all my videos are. I have over 100 videos now, between sort of 10 to 15 minute tutorials on these kind of concepts, as well as all of these talks. You can find me on social media. I'm on Blue Sky, LinkedIn, Instagram, and Facebook if you want to reach out to me. And, this is not an ad, but I would definitely encourage folks to pick up a copy of the book if you want to learn about digital currencies, security, and how to keep yourself safe in that space. So that's available on Amazon in ebook and paperback. I am also expanding to some other retailers as well. And if you don't feel like you want to pay, or you don't have the money to pay, you can read the individual chapters for free on GitHub. But the nice ebook and the nice paperback do help support the work that I do. I love to learn and teach. This is one of my favorite things to do, is get up in front of people and enthusiastically talk about all sorts of code and security stuff. So I'm here to help if you have questions.
You mentioned the waiting for the proof of stake. And so if someone put in, say, 256 versus 32, would they be more likely to be the validator, or is it still sort of random?
So there's still some randomness to it, but they're more likely to be chosen as the validator. So the idea is that anybody that is a validator with the minimum stake can theoretically be chosen in any given round. Of course, for decentralization and fairness, but you want to reward people that put more stake and sort of more skin in the game, so to say. So you're more likely to be chosen if you put more stake in. And that actually is very similar to proof of work. So the idea with proof of work is, since you're doing a bunch of guesses, essentially a bunch of hashing, the more computing power you put into the network. So if you have a giant server farm and you have 5,000 specialized processors running this, you're way more likely to be chosen than somebody that has one running in their bedroom. Now, it can and does happen that sometimes the person running the one in their bedroom happens to be the one to find the hash, to find the block. but it's very unlikely. The more computation you put in, the more likely you are to be rewarded and find block. And it's the same thing with proof of stake. The important thing is that the mechanisms are random enough so that you can't just game the system and get yourself to be picked every time. Because if that was the case, then you can manipulate the network to do what you want. You could try to break the rules. You could try to very subtly alter consensus in some way. And we definitely don't want that.
Sorry, I'm much less educated on this type of stuff, but just following up on what you just mentioned, then it sort of makes sense for like the people that have just one device versus like the server farms and whatnot to sort of, I'm assuming this is what happens, but you can pool together all the people that just have like a single device and whatnot, pull together all their performances to work together to compete with the...
Exactly. That's actually a very, very common tactic. They're called mining pools. And so you'll generally have an organization of people that are all chipping in some amount of computation power.
Yeah,
and
thinking of all of this as like a lottery system, it's like, okay, well, when people are playing the lottery, like say your coworkers and whatnot, sometimes you pull together your money and you buy a bunch of tickets, and then if you win, you split it. And I'm presuming that's what the end goal is, that like you win it, but you split it between all the participants.
Exactly. Yeah, so that's how mining pools work, and that's also how staking pools work. So, for example, if you're an individual validator on Ethereum, you have to have a minimum of 32 ETH, which is actually a fair amount of money. I want to say that's north of $100,000, but I'd have to look it up. You don't want the rich to just run the system either, even though that's kind of what happens with both proof of work and proof of stake. But with the pools, you chip in some amount, and if your pool wins the race, then they split it between everybody based on how much they put in. So like if I put in 2 ETH, someone puts in 0.5, let's just say it's a 3-person pool, the other person puts in the balance, they're still going to get most of the cut. But that made it so they could all participate in some way. Same with proof of work, right? Like if you're a person, you have one ASIC running in your bedroom, you are super, super, super unlikely to win a block by yourself. It's happened, but it's extremely rare.
This is just a lottery.
Yeah, it's because it really is. I mean, it's like a cryptographic lottery.
Yeah.
And, but if you all pool together, now your whole pool is maybe likely to win a block, and you just get a small cut of that. So it's sort of like, do I want to see if I can win the lottery every 10 years or get a tiny little bit every month?
Yeah.
Does that make sense?
Yeah.
Any other questions? And I'll be around to chit chat after too. I'm just thinking questions for our stream and everything before we sign off. All right, thanks. Yeah, no, I talked a lot, so. Yeah, really appreciate it, everyone. Thanks for coming out today. It's a lot of fun.